Hello everyone, I'm Molly, and I will be presenting to you my chemistry honors video. Now, in this video, I had to solve problem number 1, which is an endothermic reaction. Now, endothermic meaning that the reaction was taking in heat or absorbing heat energy. Now, the problem was a hot gas surrounds a reaction chamber and supplies the heat required for the endothermic reaction below to proceed. How many grams of glucose will be produced if 5.25 grams of carbon dioxide and 1.75 grams of water react completely? Calculate the final temperature of the surrounding argon gas if its initial temperature is 500 degrees Celsius. Calculate the final pressure of the gas if its initial pressure is 1 atmosphere, assuming that the volume remains constant. Now, here is a diagram or a visual that goes along with the problem. Now, I will first introduce you to the equation that we used in this problem. As you can see, the reactants are carbon dioxide and water, which produces the product of glucose. Now, you can also tell by looking at this equation that it has to be balanced. At this point it is not balanced. So if this equation is balanced, it has coefficients of 6 except for glucose. Now, you can check this by adding up all the carbon, hydrogen, and oxygens on both sides, and you can tell that this is balanced because there are 6 carbons on both sides. There are both have 12 hydrogens, and there are 18 oxygens on both sides. So now let's look at our first part of the question. How many grams of glucose will be produced if 5.25 grams of carbon dioxide and 1.75 grams of water react completely? Now, to do this, we have to find the limiting reactant. Now, what is a limiting reactant? It is the reactant that determines the amount of product produced. So this is where the values of our reactants come in. So in order to find the limiting reactant, we'll have to go from grams of one reactant to the grams of the other reactant. So we can go from grams of carbon dioxide to grams of H2O. So here you can see the 3-step conversion that I took to go from grams of carbon dioxide to grams of water. Now, I started off with 5.25 grams of carbon dioxide, and then I went into, and then I stated how many grams were in 1 mole of carbon dioxide. Then I went into the mole ratio. As you can see, there are 6 moles of carbon dioxide, and there are also 6 moles of H2O. So that is the mole ratio, which is 6 to 6, or which can be reduced to 1 to 1. And then lastly, I went into how many grams were in 1 mole of H2O. So after multiplying the values on top and then dividing that by the multiplied values on the bottom, we get 2.1477 grams of H2O. Now, look at our value for water. We only have 1.75 grams of water. Now, it says that if we have 5.25 grams of CO2, we need at least 2.1477 grams of H2O to produce glucose. But like I said, we only have 1.75 grams. So in this case, our limiting reactant is H2O. Now we can go back to the question, how many grams of glucose will be produced if 5.25 grams of carbon dioxide and 1.75 grams of water react completely? Since we know our limiting reactant, we can now solve this problem. So in this case, we can go from grams of H2O to grams of glucose. So here is another 3-step conversion, which is very similar to the last 3-step conversion that I just laid out for you. So here I started off with 1.75 grams of H2O, then I went into how many grams were in 1 mole of H2O. Then I went into the mole ratio again. There is 6 moles of H2O, and there is only 1 mole of glucose in the whole equation. And then I went into how many grams were in 1 mole of glucose, again, for the ending. And after multiplying the values on top and then dividing them from the multiplied values on the bottom, I got 2.92 grams of glucose. And that is your answer for how much glucose is produced after the reactants react completely. The next part to this problem is to calculate the final temperature of the surrounding argon gas if its initial temperature is 500 degrees Celsius. In order to do so, we have to go through two steps first. So the first step is we have to figure out how much heat was absorbed or released in the reaction. So like I said, this reaction was an endothermic reaction, meaning that it was absorbing heat or taking in heat. So now let's look at glucose. Now glucose, it's the product of the reaction, so you could say after the heat was taken in during the reaction, glucose was produced. So that's why we're going to look at glucose right now. So to find the heat, to find the amount of heat that was used during this reaction, we will have to find the heat of reaction for glucose. And now the heat of reaction is the amount of heat released or absorbed by 1 mole of a product. So in this case, in this problem, we were given that the heat of reaction for glucose was 2,540.962 kilojoules per mole of glucose. So we can leave that there for reference because we'll need that later. So ask yourself this question right now. What do you know about glucose so far from our recent calculations? Well, all we know so far is that we produce 2.92 grams of glucose. Now, because the heat of reaction uses moles, we have to use moles too. Now, 2.92 grams is not moles, so we have to convert the 2.92 grams of glucose into moles. And this is just a simple one-step conversion. And after solving this, we get 0.0162 moles of glucose. Excuse me. So, 0.0162 moles of glucose is not our answer. It is actually just the equivalent of 2.92 grams of glucose, but just in moles. So, to find out how much heat energy was taken in by the amount of moles, which is 0.0162. We must times it by the heat of reaction of glucose. So here I have it laid out for you, and after multiplying it, we get 41.21 kilojoules per mole of glucose. I should have written out glucose. So now I'll put that here in the corner for reference later, because we will definitely need this amount of heat. Now, I told you there were two steps in solving this part of the problem. So now we will start our second step. So our second step is to solve for the temperature change of the argon gas. So to solve for the temperature change, we will use the formula delta T equals Q over M times C. Now we already have Q, which is the heat that we calculated in our previous problem. So that is 41.21 kilojoules per moles of glucose. Now, we don't have our mass, and we don't have our specific heat capacity yet. But actually, the specific heat capacity of argon gas, argon in the state of gas, was given to us, and it is 0.5203 joules per grams times Celsius. Now, for mass, we were given the information of 7.88 moles of argon. Well, mass is measured in grams, so we have to convert the moles into grams. So this is also a simple one-step conversion. So that would be 7.88 moles of argon times 39.95 grams of argon, because there are 39.95 grams in 1 mole of argon. So after solving that, we get 314.806 grams of argon. So now we can replace that with our mass. So with this new information, we can substitute all of the information into the equation. So we have 4,121 joules per moles of glucose on top. Now on the bottom, we have 314.806 grams of argon times 0.5203 joules per grams times Celsius on the bottom. Now, you may be wondering why I changed the 41.21 kilojoules to 4,121 joules. They're exactly the same, just one is, you could say, expanded. And I did that because there was joules in the unit of joules was in the specific heat capacity of argon. So just to make life easier, I made the units the same so they could cross each other out. So after solving this, the change in temperature is 251.6 degrees Celsius. So now we can also put that in the corner for reference because we will be using this change in temperature later. So now we can actually solve for the part, calculate the final temperature of the surrounding argon gas if its initial temperature is 500 degrees Celsius. Well, now the question is, what do we do with the change in temperature and the initial temperature? Do we subtract it or add the change of temperature to the initial temperature? Well, in this case, in this reaction, the reaction was gaining heat because it's an endothermic reaction, which means that the gas was losing heat. So we will subtract the change in temperature from the initial temperature, which will give us the final temperature of 248.4 degrees Celsius. And converting that into Fahrenheit, we will get 479.12 degrees Fahrenheit, and for Kelvin, we would get 521.55 Kelvin. So our last part to this problem is calculate the final pressure of the gas if its initial pressure is 1 atmosphere, assuming that the volume remains constant. Now, since the volume is remaining constant, we can use Gay-Lussac's law, which is pressure 1 over temperature 1, or initial temperature, that equals pressure 2 over temperature 2, which is our final temperature. So here we can substitute everything, which would be 1 atmosphere over 500 degrees Celsius equals pressure 2, because that is what we were finding. We were finding our final pressure, over 248.4 degrees Celsius. Now, before cross-multiplying, before solving this, we have to convert Celsius into Kelvin. And we are doing that because we are trying to avoid having any negatives in our denominators. And Kelvin is the only heating scale that does not use negatives. So here is our converted, you could say, equation. So that is 1 atmosphere over 773.15 Kelvin, and that equals pressure 2 over 521.55 Kelvin. And after cross-multiplying correctly, you get the final pressure as 0.6745 atmospheres. Now, we are actually done with this problem now, but just a quick review, we will go over the 3 parts of this problem. So how many grams of glucose will be produced if 5.25 grams of carbon dioxide and 1.75 grams of water react completely? And we received an answer of 2.92 grams of glucose. Now our second part is calculate the final temperature of the surrounding argon gas if its initial temperature is 500 degrees Celsius. Now we said that the final temperature is 248.4 degrees Celsius. In Fahrenheit, it would be 479.12 degrees Fahrenheit, and in Kelvin, it would be 512.55 Kelvin. Now, the last part is calculate the final pressure of the gas if its initial pressure is 1 atmosphere, assuming that the volume remains constant. Now, again, we used Gay-Lussac's law to solve for this, and we found out that the final pressure would be 0.6746 atmospheres. That concludes the end of the video. Thank you for listening. I hope you enjoyed.